Hi, everyone. Welcome to another Origin seminar this week. We have Caeley from Boston University, and Caeley is an NSF graduate research fellow at Boston University working with Catherine Espelliot. She is a member of the ODYSSEUS collaboration and has led the magnetospheric accretion analysis of the HST Ulysses survey. Caeley completed her doctoral studies at William Jewell College in Kansas City and the University of Oxford in the UK. And she has performed research at institutions including Oxford, CERN, and Maria Matthieu Observatory. And today, Caeley will bring a presentation on characterizing the star disk cloud connection in classic Tauri stars. And the floor is yours.
Thank you for the introduction and for the invitation to give a talk. And thank you for the time to be here. I appreciate it. So today I'll be talking about the bulk of my work, which has come out in the 3 papers this year, and characterizing the star Tauri stars. So here I'm looking at the very small scales of the stellar magnetosphere, but also drawing connections to slightly bigger scales and even bigger scales in the star formation. Done collaboration. So to start, I just want to get the broad picture of low mass star formation. So by low mass star, I mean stars that are about 2 solar, and in most cases, on molecular star formation or on kind of big scale overdense regions in the ISM, and the star formation starts with the stellar core of an overdense region that collapses under gravity for some time. Is the sound quality better?
Yeah, I think you need to turn that off.
Turn this off?
Yeah.
This is already off.
It's somehow connected.
I mean, this one should working. Can people hear us well now?
Yes.
Okay, good. Thank you.
Okay. So just to summarize what I've said, we're looking at systems that will have stellar masses of about 2 solar masses or less, forming on molecular filaments. So you have, from the beginning, you have this big scale structure with some kind of coherent velocity and mass structure that collapses under gravity and eventually forms an enshrouded protostar. So this is kind of the class 1 stage where you have a central massive star or low mass star, but it's still optically blocked by a surrounding cloud. And then eventually this cloud collapses into a disk, and then your central star becomes optically visible. So this is the visible classical T Tauri star stage. And at this point, the disk material is still accreting inwards towards the star. And in the very central regions, this star has a very strong magnetic field. It's on the order of a kilogauss, so 1,000 times that of the sun. And it can cause this inner disk material to flow along the field lines and accrete onto the star. At some point, substructures are also likely to form, either from planet interactions or just other disk instabilities. So this is kind of one of the most well-known things about classical T Tauri stars is you have these very beautiful ring and gap structures that are seen with ALMA. And then eventually this disk dissipates and you are left with a non-accreting T Tauri star that continues moving towards the main sequence. And by this point, the bulk of the planet formation should be complete because the planet forming material has dissipated. So in my work, I'm focusing on this 3rd stage, the optically visible classical T Tauri star phase. And this is where you can see the accretion process kind of most clearly. So looking at classical T Tauri stars, in more detail, this is kind of the classic overview figure. And it depicts the central star with its very strong magnetic field, typically approximated as a dipole. And this field is causing disk material to flow onto the star in magnetospheric accretion. And then at further colder regions of the disk, you have dust as well, a dusty disk. So these outermost regions are observable typically with ALMA. But as you go into warmer regions, then you start to look in the infrared with JWST and at even shorter wavelengths in my work, I'm looking with Hubble Space Telescope tests as well as ground-based optical and infrared observations. And in my work, I'm focusing on the very innermost regions. So these are scales of about 0.1 AU and below. So these are nearly impossible. They're very, very challenging to spatially resolve. But they are, it's a region of particular interest, especially in terms of planet formation. Half of all known exoplanets orbit within 0.1 AU of their host stars. And part of this is an observational bias, of course, but it is also it's also grounded in a physical reality that 0.1 AU is the most common location of the innermost planet in exoplanetary systems. So all of the mass, angular momentum evolution in these central regions are strongly affecting this planet forming environment. So the big picture question of my work is, what is the relationship between the central T Tauri star, its inner disk, and its environment? And in answering this question, I will start looking at magnetospheric accretion, so kind of this innermost of the innermost scales. I look at two accretion emission regions. One is the flow of gas as it goes along magnetic field lines onto the star. This gas is moving at free fall velocities, so it's on order of 200 or 300 kilometers per second. So this flow of gas produces very broad emission lines, and this is most easily seen in most sources in H alpha. So they are very bright in H alpha with very broad line profiles. Then when you zoom in to where this flow actually reaches the stellar surface, you get an accretion shock. This converts the kinetic energy of the inflowing material to thermal energy. So it heats the shocked region to about 1,000,000 Kelvin. So this initially emits strongly in X-rays, but this emission is reprocessed by the stellar photosphere. And ultimately, we observe this as UV through optical continuum emission. So this is an example classical T Tauri star spectrum. The HST spectrum is in black of an accreting source. And a non-accreting T Tauri star of the same spectral type is shown in gray. So kind of the clearest difference between these two is this very strong continuum excess, and it's strongest at the shortest wavelengths. And this excess is coming from the accretion shock and the associated accretion hotspot. And then here, we can also see there is an H alpha emission line, and this is what's coming from the accretion flow primarily. So this is bright in the accreting source and not bright in the non-accreting source. So in my work, I work with the ODYSSEUS and Penelope collaborations. These are international collaborations spanning 20 countries, over 100 people. And within this collaboration, I've led the accretion analysis. And the core data set of the work is looking at 67 classical T Tauri stars from the ODYSSEUS Director's Discretionary Program. So this was a really fantastic program that dedicated 500 HST orbits to observing classical T Tauri stars. So it's by far the largest and most uniform sample of UV through near-infrared observations to date. And my core analysis of this data set is applying models of the accretion flow and the accretion shock to these ultraviolet through infrared observations. So first I'll introduce the accretion flow model. It makes a couple very fundamental assumptions. One is that the stellar magnetic field is a pure dipole, and that is actually a reasonable assumption to make these distances from the star. And the other assumption is that the system is axisymmetric. So what that implies is that the stellar magnetic moment is aligned with the stellar rotation axis, and both of these are perpendicular to the disk. So when you fit this model to observations, you can constrain 5 parameters of the magnetosphere. The first is the viewing inclination of the system, called Imag. So it's just the angle between the axis and your line of sight. Another is the magnetospheric truncation radius. This is the point in the disk where the magnetosphere's magnetic pressure balances the ram pressure of the accreting material. And this is an important point for planet formation, and this is kind of the main thing that describes the physical extent of the magnetosphere. You can also constrain the width of this inflow, the mass accretion rate onto the star, and the temperature of the flow. Then the second model is the accretion shock model. So this is once the gas has actually reached the stellar surface. It is a one-dimensional non-LTE model with 3, it includes 3 emission regions. One is the pre-shock region, one is the post-shock region, and one is the heated photosphere. And this shock produces an associated hotspot on the stellar surface. And an important part of this model is that it doesn't make any assumptions on the shape or location of this hotspot. It just constrains the total surface coverage, F hotspot. We can also get another estimate of the mass accretion rate onto the star, as well as the temperature of the hotspot. And we know from both models and observations that hotspots are not uniform. They have density gradients. Might look something like this, where you have regions of higher density and regions of lower density in this hotspot. And the accretion column that would produce such a hotspot looks something like this. So you have the inflow that has some gradient and the energy flux density represented by cursive F here. For computational reasons, we approximate this flow structure using 3 discrete accretion columns with low, medium, and high densities, and each has their own associated surface coverage. And using the accretion flow and accretion shock models, I do this in an iterative process where the output of one is the input of the other, because we want to build a self-consistent picture of this whole accretion process. So this is an example of an accretion flow model fit to H alpha. So this is for one source in the sample, CS CHA. The observation is in black and the best model fit is in red. And this is an example shock model fit to the same source. So here we have the HST spectrum in black, a non-accreting template photosphere, so same spectral type, no accretion, in gray. And this source was best explained with a 2-component hotspot represented by the yellow and orange lines. And when you add all of this together, you get the red total model. So one important part of accretion is that this accretion emission is irradiating the surrounding disk, and that is going to drive a lot of the chemistry you observe.
Can I ask a quick question? Do you get the same mass accretion rate?
Yeah, so that's actually this is from my first paper of this year. This was the first time we did a really systematic comparison of these 2 separate models. And thankfully, yes, they provide very consistent accretion rates. The HST observations and H alpha observations are usually separated by about a day or so. And so most differences between the models can be explained by kind of temporal variability, but they are quite consistent. It's a great question. Yes, so this emission is irradiating the surrounding disk and driving the surface chemistry. So this is an example JWST spectrum from a paper that just came out from our group. And in this paper, we found that the accretion emission is affecting the carbon chemistry you're observing. So if you have really high energy, ultraviolet bright accretion emission, you're going to see less carbon in the disk due to photodissociation. So if you want to understand the disk chemistry, it's important to also understand what the accretion, what the incident radiation is looking like. So this is now showing the accretion spectra in absolute units for the full sample. I've highlighted for individual targets, but all of the lines show the full sample. And the first thing of interest is that this absolute accretion emission is spanning 4 orders of magnitude in different sources. And that's not purely explained by just the spectral type of the source. It's not that the brighter ones are always higher mass. Here, this yellow curve is from an M0 star, and it's about as bright as this purple curve from a G9 star. So accretion can have a really significant effect on the incident radiation that's not just explained by the stellar mass. And another important component here is that the accretion spectra are not simple black bodies, because you're taking, you have a multi-component hotspot. It's often not well represented by just a 1 temperature black body. However, that is typically an approximation that is made in kind of disk chemical analyses. So in ongoing work with Umagorti, we are looking into the actual chemical effect of this diversity of incident irradiation on the disk.
I have a question about the hotspot size. And then do you have a 2 temperature for the hotspots, the temperature distribution in the hotspot? How large can the hotspot can be?
That's a great question. So from other observational work, there's kind of tentative upper limit on a reasonable surface coverage of about 40%. But that's not the typical value. I have a backup slide I could maybe show later of the typical surface coverage. So it's usually less than 10%.
But there are known cases that over 50% could be hotspot. I mean, the hotspot.
Yeah, no, there are definitely in cases it could be higher, but it's not common. So in my analysis, I limited it to be 40% or below, but there are maybe 9 sources that push that limit. And it's unclear if that is actually physical or not. It kind of requires additional study. Usually it's less than 10%. And then moving to another result, also from my first paper of this year, we found that inner gas disks extend much closer to the star than previously thought. So this is described by the magnetospheric truncation radius, RMAG, which sets where, how close to the star this disk extends. And here I'm showing a histogram of the magnetospheric truncation radii for the full sample, and these are in units of stellar radii. So in previous work, the kind of first order approximation that everyone has used is that RMAG is 5 stellar radii for all sources. It's kind of like we haven't, this region is really hard to resolve. So it's kind of been just the best guess. So this is the first time that on a really large scale, we've characterized through measurement the size of the magnetosphere. And clearly they tend to be much smaller than this previous assumption. In fact, it's almost half the size. So the median radius is 2.8 stellar radii compared to the previous assumption of 5. And the actual location of RMAG is important for short period planet formation. So theoretical work has shown that the magnetospheric truncation radius can trap planets. So if you have kind of type 1 migration occurring where a planet is migrating from Lindblad torques, it'll move in and it can be trapped at the truncation radius, and it will halt before it accretes all the way onto the star. And so an implication of this small RMAG value is that it can provide a formation route for ultra short period planets. These are planets that orbit with periods of about a day or less. So they are very, very close to their host stars. It's on the order of 0.02 AU. So they're very close to the host star. And interestingly, the median magnetospheric truncation radius is equivalent to the median location of ultra-short period planets. So previously, because our mag was assumed to be larger, ultra-short period planet formation theories were usually used kind of a two-step process. So first, the planet would migrate in, stop at our mag at the truncation radius, and then you would need some secondary force to bring it all the way into its final location. So the secondary force could be tidal interaction with the host star, or it could be planet-planet scattering, but you needed some other force to explain how these planets were so close to the host star. And usually they required like timescales of 5 billion years to get to the final location. So to look into this, I compared the magnetospheric truncation radii, now shown in terms of astronomical units instead of stellar radii. I compared this to the observed ultra-short period planet locations. And clearly these distributions are not equivalent. I think it would be more suspicious if they were equivalent. These planets are extremely rare, so you really just need a few systems where all of the stars align and the planet ends up making it all the way in. But anyway, to conclude this, this result that the truncation radius is small provides just a simpler formation route for ultra-short period planets because you don't need that two-step process to bring them to the final location. Okay, now moving into the second part of this talk.
Can I ask a couple of questions?
Yeah,
like
of course.
I said, two questions. So one, I mean, can you talk a little bit more about the uncertainties on our mag and like exactly where it pops out of the models?
Mhm.
And then I guess, you know, in terms of your argument about it explaining the ultra short period planets, I guess, given that they're a sort of separate population, what would be the explanation for why there's not a smooth distribution if the typical radius is so much further in than we previously thought? Like, why aren't all the planets just, you know, piling up there?
Okay. So to your first question, the truncation radius comes from the accretion flow modeling. So it's a model fit to H alpha observations. So it's one of the 5 parameters. We calculate a grid of models and do kind of a chi-squared reduction to get the truncation radius.
Yeah, so I guess, you know, if I were to look at like a triangle plot and see how it varied with other parameters,
Right,
like
yeah.
what are the things that typically give rise to the uncertainties on your measurement or your inference of RMAD from that model? Or like what in the spectrum is controlling the inference that it's much smaller than previous claims?
So I guess one answer to that is that I did make a corner plot and look for degeneracies between parameters, and there's not really strong degeneracy between really any of them. It's only, yeah, I don't need to go into details, but the truncation radius is not heavily degenerate with anything else. I looked into whether, well, I can go into lots of details, but I guess one of the main changes in the H alpha line profile, if you change RMAG, is if it's a bigger truncation radius, the line flux is brighter, but it's not quite as simple as that. But that's the main change, is kind of the flux. Can you remind me your second question?
And then I'm just wondering about, given that this RMAG distribution is kind of right peaks towards small radii, why would it be that you have just a small rare population of planets that migrate to the inner edge when most don't, if it's not a separate mechanism, I guess?
Right. So I think I'm planning to look into this in postdoctoral work, but my current thought is that there are kind of 2 separate mechanisms going on. So the truncation radius can trap planets, but so can the dust sublimation radius. And that is normally closer to 0.1 AU. So my thought is that most commonly it's the dust sublimation radius trapping planets. But in the cases where they move in further, it would be the magnetospheric truncation radius determining that final location. Great question.
Actually, going back to the question, I was actually wondering, you see, what is the uncertainty on our marker? What was the uncertainty?
So I have, let's see, let me see what my next slides are. Okay. So uncertainty on RMAG is kind of multifaceted. So there is uncertainty on a given measurement. I don't remember the exact value, but it's less than 0.1 dex on an individual observation. It's a pretty small uncertainty in terms of like the statistical uncertainty. But we look at multiple epochs of observation of each source, and we see that the truncation radius changes with time, which is fully expected. It's just if the accretion rate is changing, the ram pressure on the magnetosphere is changing. So if the accretion rate decreases, the magnetosphere can increase. So over time, there is variability in a given system of the truncation radius, which, yeah, but it's not like really massive. It's on the order of 33%, I think, the temporal variability. And here the truncation radii that I plot here are the the weighted average for a given source. So it's kind of a representation of its typical value. Did that answer the question sufficiently?
I have a sorry, so very quick question. So when it varies, when you have a stronger accretion rate, does the RMAG actually go larger? Is there a correlation between accretion rate and then RMAG?
Yeah, so I really wanted to find that. In most cases, we only have about 4, like a maximum of 4 observations per source. So it's kind of, especially when you take uncertainties into account, it's hard to see a really clear correlation. So it should be that if accretion rate increases, then you should have a smaller truncation radius. There are definitely sources where we see that, but there aren't enough observations for me to really say that confidently. But there are specific sources where we have, where you can kind of build a more complete picture of what's going on. So there's one source that I focus on in my second paper this year, CS-CHA, that seems to show an episodic accretion process where we can kind of explain all observables with kind of a compression of the magnetosphere, a resulting expansion of the magnetosphere that's associated with outflows. So we do see it, but big picture can't really conclude yet. Any other questions before I continue? Okay, so now I'm moving to more directly to my second paper of this year. So here I looked at test-like curves of the sources to incorporate the stellar rotation information. And this was to look more closely at the star disconnection and angular momentum regulation in these innermost regions. So here, this is, again, CS-CHA, it's the same source I was showing before. You can see there's this very strong periodic signal, and from that you can get the stellar rotation period. The signal is coming both from hot spots on the surface as well as cold spots. So as these spots rotate in and out of view, you can get this rotation period. And what we really want from this rotation period is to calculate the co-rotation radius in the disk. This is the point in the disk where the Keplerian orbital period equals the stellar orbital period, rotation period, and you just calculate it from Kepler's law. And I'll discuss the importance of that in a moment. But here we're really trying to build a complete picture of the innermost regions. So you combine the results of the accretion flow modeling, the accretion shock modeling, and this test analysis to put it all together to see what the innermost regions look like. So everything here is to scale, including the temperature of the star and the hotspot. But what I am really focused on is the relationship between the magnetospheric truncation radius and the co-rotation radius. And just as a reminder, these innermost regions are really closely connected to planet formation. So it's around here, around 0.1 AU, that we see the buildup of innermost planets. And as I just showed, it's around the truncation radius where we have these ultra short period planets. So this is all connected. So the relationship between the magnetospheric truncation radius, Rmag, and the co-rotation radius indicates the spin state of the system. This has been parameterized by the fastness parameter, omega sub s. So this is just the ratio of the stellar angular velocity to the angular velocity of the inflowing material. And if you just do some algebra, you get this relation here. So to explain this more directly, we can look at this top left panel. This is the propeller regime. This is where the co-rotation radius is inside of the truncation radius. And what this means is that the star is rotating faster than the inflowing material. So the material at the truncation radius that is flowing towards the star has lower angular momentum than the star itself. What this does is produce a centrifugal force that causes an outflow of material from this inner region. And so a lot of the material actually doesn't accrete onto the star. It's instead kind of cast away. It carries away angular momentum. And any accretion that does occur is mostly occurring at high stellar latitudes. But then if the co-rotation radius moves slightly outside of truncation, you can reach a stable state. And these states are predicted from 3D magnetohydrodynamic modeling. So in this state, when it's stable, you can have really long-lived accretion flows that rotate with the star, and these have associated long-lived hotspots that also rotate with the star. But then if the co-rotation radius moves further and further away from the magnetosphere, you enter an unstable regime where accretion is a lot more chaotic, less periodic, and less long-lived. And theoretical work indicates that you should have an equilibrium spin state of a fastness parameter around 0.7. So that's in this top right panel. So what I really wanted to see is that when we measure the truncation radius and the co-rotation radius, do we see a pileup in the stable state? Do we see that most are in stable states? Or is it something a little less expected? So here I'm showing the magnetospheric truncation radius on the y-axis and the co-rotation radius on the x-axis with the expected boundaries between these different states as the lines. So dividing the propeller state where stuff gets cast away, angular momentum is carried away, stable and unstable states. And if I plot our actual observations, you see that there is not a pileup in this stable state. Actually, most are in unstable accretion states. And the colors here indicate the angular momentum change of the star. So the pink points mean that any accretion process should act to spin down the star. Green points mean that accretion should act to spin up the star because the accreting material has higher angular momentum than the star. And black points would indicate a fairly stable spin state, but clearly most of them are not black, most of them are not stable. So this was somewhat surprising. So you might say, okay, maybe these just haven't had time to accrete enough material to reach a stable equilibrium. But we don't see any age dependence. So it's not that these are younger sources that just haven't had time to reach stability. This seems to be a kind of like the long-lived state of classical T Tauri stars, that they are typically not in spin equilibrium.
That's a question. What is the age range in the samples?
It covers about 1 to 10 million years. So the oldest region, I think, is Corona Australis. The youngest is, I guess, Taurus, and kind of filling in between as well. So this age-independent slow rotation of classical T Tauri stars points to efficient angular momentum loss processes, because these stars are continually accreting. They are accretors. They are accreting material that has higher angular momentum than the stars, and yet they're not spinning up. So in my second paper this year, I explored various accretion loss mechanisms to see if they were consistent, see if these predicted angular momentum loss mechanisms were consistent with our observations or not. And I found lots of, yes. So I found evidence of magnetohydrodynamic outflows carrying away angular momentum. This includes conical disk winds that are launched from the magnetospheric truncation radius. So they're just flowing out in kind of a cone, carrying away angular momentum, as well as magnetospheric ejections. So this is from reconnection events in the magnetosphere, causing these kind of magnetic bubbles to carry away angular momentum. Also, as I said, found evidence of episodic accretion, which can produce outflows that carry away momentum. And finally, our observations were consistent with accretion-powered stellar winds. So this is where you have a conversion of the accreted energy being converted into kind of energy in the stellar wind that gets carried away. So these results were somewhat surprising. Like most spin evolution models kind of assume that systems reach spin equilibrium, but they seem to not. But it is also consistent with observed stellar rotation rates. So these sources are observed to have slow rotation throughout the whole disk-bearing phase. It's only when they reach that last stage where the disk is dissipated that they really spin up to their kind of zero-age mean sequence rotation rate. So again, just caution for any spin evolution models, they are not typically in equilibrium.
Let's get a quick question. What are you using for our star?
That's a good question. So all of the stellar parameters in the sample were derived by the same person all consistently from, they were derived from VLT X-shooter spectra. So yeah, fitting photospheric templates to the stars to explain the photospheric absorption lines to get all the stellar parameters.
You have, yeah, it's log G. It's
yeah.
Is there, and then it's a spectral type mass.
Mm-hmm.
Okay.
Mm-hmm. Yeah. Okay, so going back here, now I'm going to show the temporal variability of the truncation radius. So here, this is just showing measurement uncertainties. So this can kind of give a sense of the measurement uncertainty of these truncation radii are usually pretty small compared to the point size here. But if you look at temporal variability, I'll flip back and forth. The variability in time can be pretty significant. In particular, some sources may have a typical value, for example, in an unstable accretion state, but in kind of for short periods, they can jump to a propeller state, for example. So if you categorize a star in one state, that doesn't mean that it's always in that state. It is variable, and that is fully consistent with predictions from the 3D magnetohydrodynamic models as well. Those predict variability in the truncation radius. And this variability is on the order of days, so it's fairly fast as well. Okay, moving to the light curve morphologies. Another topic of interest is dipper systems. So these are sources where their light curves are dominated by dips in the light curve. And this is caused by some occulting material going in between your line of sight to the star. And the typical idea of how dippers are formed looks something like this, where you have usually the stellar magnetic moment is tilted from the stellar rotation axis. And this can have two effects. One, it can produce a disk warp that elevates material at the truncation radius above the disk surface. And you can also have a potentially dusty accretion column where if you look through either the disk warp or the accretion column, it's occulting your line of your view of the star, but it's only at some phases. So as the star rotates, as this flow rotates, you can also get a full clear, unobscured view of the star. So that's kind of the general picture of what causes dippers. And these are really interesting for looking into asymmetries in the disk. And it can also provide some information on the actual dust content of the disk if you look at kind of the profile of the obstructing material. So one finding is that dippers tend to have viewing inclinations above about 50 degrees. So IMAG here is the viewing inclination from the accretion flow model. And a system is a dipper if this colored point falls below this bottom line. So here you can see that these have relatively high inclinations. This one source over here that's more low inclination is not a true dipper. So this makes sense. It's consistent with expectations. If you're viewing a source fairly face on, it's unlikely for this material to occult your line of sight. But a more surprising finding is that dippers do not only occur in the propeller state. So to break that down a little, this classic picture assumes that the magnetospheric truncation radius is about equivalent to the co-rotation radius. So it's fairly common for someone to say the source is a dipper, therefore it's a propeller. But that's not actually what we find. So here the different colors represent the different states. And again, points are dippers if they are below this line. And clearly dippers, they don't show a dependence on this relationship between the magnetospheric truncation radius and co-rotation. So in this classic picture, you would kind of expect all of the dippers to be around here, but there's not really a dependence. So this requires some kind of new paradigms for understanding the cause of these dippers. And that's something I want to look into in my postdoctoral work if someone gives me a job. So yeah. Moving to the third part of this talk, this is associated with my third paper this year. Now I'm looking at bigger scales to look at the star-cloud connection. I guess before I move on, were there any questions from the last? So here, I focused on the lupus star-forming region. Shown here, these white points are the stars in my sample. Lupus has 4 main subregions, where lupus 3 is the most populated by far. And here I incorporated the 3-dimensional coordinates of each source, so RA, DEC, and the Gaia distance, to look for relationships between sources that are close by in the star, and also taking into account the host cloud as well. And lupus is between 1 and 3 million years in age. So if we do see a star-cloud connection at this point, this would be one of the, typically when we see star-cloud connection, it's in class 0, class 1 sources, so very young sources. So if we see correlations here, that is particularly interesting given the somewhat older age of these sources. So again, going back to the beginning, 70% of stars form in filaments, and filaments often have kind of some coherent velocity structures, maybe some coherent rotation. And so that can create a connection between stars formed from the same filaments. Lupus is particularly interesting because its star formation is directly linked to really large-scale coherent forces. So here, this is from a paper focused on lupus 1. And this showed that lupus 1 is kind of squeezed between 2 shells. So one is the upper Scorpius H1 shell that was produced by a supernova explosion. And the radius of this shell is about 36 parsecs, so really large scale. And the other one is the upper Centaurus lupus wind bubble. A long time ago, there was a supernova explosion from the same region, but at this point, this is driven by B stars in this region. And the lupus star-forming region is squished kind of right at the interface between these two. And it's thought that lupus 1, the lupus 1 filament and the associated star formation was produced by this interaction between these large-scale forces. So if we're going to find spatially related sources, this is probably, a great place to look because there is already this known large-scale force. So I looked into everything I measured, I looked to see if it was spatially correlated. And the clearest thing that I found was that the viewing inclinations of the systems are both spatially correlated and non-uniform. So first I'll just show kind of the bulk result. So if you look at a sample of inclinations, if they're randomly oriented in the sky, it should be uniform in cosine, and the cumulative distribution function should look like this gray line. It's just a straight line from 0 to 1 in cosine. And based on my sample size, anything consistent with uniformity should fall in the shaded gray region. And if I look at 8 different star-forming regions, including lupus, but 7 other star-forming regions, the viewing inclinations are consistent with being uniform within uncertainties. So the observed distribution is in black with its associated uncertainties. But if you look only at lupus, it is strongly non-uniform. So this is showing the 95% confidence intervals here, and clearly they're not overlapping. So instead of being uniform, the lupus sources tend to be viewed more edge-on. So this is the bulk result looking at all inclinations together. But if you look at them in the sky and in 3D space, they also show spatial correlation. And this is on scales of about 3 parsecs or so. So the clearest example is these 5 sources in the southeast portion of lupus 1. These 5 all show very similar inclinations. These are indicated by the colors. The color bar shows the inclination. So all of these are somewhere around 50 degrees inclination. Similarly, in the northwest part of lupus 1, most of these tend to be much more edge-on, closer to 70, 80 degrees. If you look at lupus 2, these are kind of intermediate between those, all kind of this orangey color. Lupus 3 tends to be quite edge-on. These sources tend to be viewed pretty edge-on. They're orangey yellow colors. And also in lupus 4, they tend to be this orangey color. So this is showing you in the plane of the sky, but in the paper, we do a whole long analysis looking at the 3-dimensional space and incorporating uncertainties in the Gaia distance and uncertainties in the viewing inclinations. And these correlations still last. They are robust against those perturbations. So we can group sources in 3D space by their similar viewing inclinations. And if you place these in context with these 2 large-scale forces, here this shaded region shows the extent of the upper Scorpius H1 shell. This is the one driven by the supernova explosion. Here, it's hard to see in projection, but in 3D space, it produces a pretty natural division between the lupus 1 northwest sources that are fairly highly inclined and the lupus 1 southeast sources that are more lower inclination. And then also, if we look at the stellar wind-driven bubble from Upper Centaurus lupus, that's shown by these dashed lines, there's also a connection with the position angles of the disk. So I didn't mention this before, but these arrows on each source are the disk position angles. These were measured from the gas observation, so it's resolved between 0 and 360 degrees. And you can see here, kind of clearest in lupus 4, that all of these tend to be, kind of up and down position angles, which is approximately parallel to this stellar wind-driven bubble. So that indicates kind of a connection between this large-scale force and the observed disk morphology. And additionally, if we look in 3D space, you can kind of explain be biased towards high inclination. So like I said, in conglomeration, the inclinations tend to be more edge-on. They're not uniform in the sky. And that's kind of dominated by the Lupus 3 region. So if you look at the Lupus 3 region in the plane of the sky, it kind of just looks like a blob. There's not a lot of clear structure there. But if you look in 3D space, here I'm showing kind of view from the side where this dashed line shows the line of sight to Earth. You can see that our line of sight is almost perfectly aligned with a filamentary distribution of these stars. So rather than being a spherical blob, they're actually this elongated structure that presumably formed from a filament. So I'll just show this video to make the 3D structure a little bit more clear. But the conclusion from this is that we are looking kind of right down the barrel of this filamentary structure. And this can be explained by filamentary collapse. So if you have the major axis of a filament, both observations and models indicate that prestellar cores tend to be elongated along the major axis of the filament, and their rotation axis tends to be perpendicular to the major axis of the filament. So if you're viewing right down the major axis of this filamentary structure, you're much more likely to see a system edge-on than face-on. Face-on would mean looking right down this rotational axis. So yeah, I think this is my last kind of slide. So because the Lupus 1 region is millions of years in age, this is showing a pretty long-lived connection between the initial conditions of these star formation and there's current kind of structure. And it's extra surprising because these magnetospheres are only about 0.02 AU in size. So these are really small scale structures, and they're correlated over scales of about 3 parsecs. So this is pretty surprising. I tried a lot of ways to see if this was fake because I wasn't really expected, and I wasn't expecting to find this. And so I guess one last kind of bigger scale implication here is that if this non-uniformity of system inclinations were to propagate to the exoplanet kind of orbital inclinations, then that would have a pretty significant effect for occurrence rate corrections. Because if you are assuming that exoplanet orbits are fully uniformly distributed, then when you correct for, okay, we mostly see edge-on exoplanets. How do we infer the total occurrence rate? If you're just assuming it's uniform, then that might not be true if you're looking at only certain regions of the sky. It does seem to be, if you look at all regions of the sky together, a uniform description is reasonable. But if you're looking at a specific region of the sky, that may not be the case if this non-uniformity continues. But that's kind of an even next step. So in previous work, we've seen, very, very young systems are spatially correlated. Now we're seeing also this classical T Tauri star phase shows some spatial correlation. So then the next step is, okay, does that then continue, or do random perturbations kind of even that all out? So going back to the main question, what is the relationship between the central T Tauri star, its disk, and its environment? We've seen that the magnetospheric accretion process is central to the star-disk connection in a number of ways, including the mass transport, the angular momentum transport, short period planet orbits, where that disk is truncated, important in terms of disk irradiation. And additionally, the magnetospheric scale, very small scales, is connected to parsec scale cloud properties, at least in Lupus. And in future work, I want to see if that extends to other star-forming regions as well. So now I'll just leave up kind of the main conclusions. These papers were pretty chunky, so there's a lot more if you want to look into them, but these were the results that I thought were kind of most interesting. Thank you again for being here. I appreciate it, and I'm happy to answer any questions.
So we have a question online. Lama, do you want to speak out or I can?
Yeah, sure, I can. Thanks for a great talk, Caeley. I was wondering, from the accretion models, do you estimate the total magnetic field strength for each of the stars? And if you do, then do you find any correlation with the wind strength that you find from the absorption?
It's a really good question. We do estimate the stellar magnetic field strengths. I would say it's really a rough estimate because it's based on the parameters from the flow model, which assumes a perfect dipole. It assumes everything is axisymmetric. So the paper does give those estimates, but I wouldn't put too much weight in them. And I've not at this point calculated the actual wind strength. In my study, I just looked to see whether there was evidence of winds or not. So it's kind of a binary. But I haven't quantified the density of the wind or the velocity. There's kind of too many moving parts for that, with the available data. But that's a great question and good future work.
I have a connected question between the model and the lupus results. So you're measuring IMAG, which is a proxy for the alignment of the dipole field, which you are assuming is aligned with the stellar rotation axis. And then you also have in the lupus region, you have some disk measurements, but it looks like the disk measurements have more dispersion than the IMAG measurements. Is that accurate? I mean, I'm just looking at vectors. So
yeah. So other people, specifically Aizawa et al. 2020, I think, looked at the disk position angle and did find that they were non-uniform as well. They were looking at the lupus 3 region and found that they were not non-uniform. They tend to be kind of perpendicular to the magnetic field in the region.
But they look, I guess I'm right. You're rightly, saying it's surprising to see the correlations going from very large scales to small scales. But I'm wondering about the intermediate scales of the disk and whether or not do you have like a...
I have a backup figure for that.
You said you had many backup slides, so I'd love to see the dot product of the disk versus
Yeah, so this is what I have. This is what's in the paper. So the gas disk inclination, partially from HPRO, partially from earlier work, versus the magnetospheric inclination. So in this comparison, we do see that they are typically within 20 degrees of each other, but the tendency is that the magnetospheric inclination is higher than the disk inclination. In the paper, I discuss some observational biases there. So typically, CO is detected. It's always detected in transitional disks in the sample. It's not always detected in full disks. So that shows kind of a relationship between the dust that's obscuring and the gas you see. So these disk studies specifically removed any sources with disk inclinations greater than 70 degrees. So there's kind of an inherent bias against highly inclined disks. But what I'm finding is highly inclined magnetospheres. So it's kind of hard to compare the measurements directly. They're correlated, like the Pearson correlation coefficient is like 0.6. So, there's some correlation there, but
And do you have an independent measure of the stellar rotation axis from the other paper? Or are you just always assuming, right, when you're comparing RMAG to R co-rotation? Right, that's assuming that the IMAG tells you the stellar spin direction.
So it's not really sorry, can you repeat the question?
So if I understood correctly, your model is that there's a dipolar field that's perfectly aligned to the stellar rotation axis.
Yeah, they're never directly connected though. So the stellar rotation, it's not like from V sin I or anything. It's just from the light curve periodicity. So we don't ever make any direct use of the stellar rotation axis at any point.
But I guess you're always inferring that it is perfectly aligned. I guess so. I'm wondering about things like, the classification of the, right, going from small scales to large scales, whether or not you expect the disk and IMAG to be perfectly aligned. Seems like the intermediate point there would be the stellar spin. But you're assuming that those are perfectly aligned. But then there's the other result that shows that all the sources lived at slower rotation periods relative to the co-rotation radius. But that's assuming that the disk and the stellar spin are also perfectly aligned.
Yes, the model makes that assumption.
I guess you could test, in principle, if these are very well characterized stars, you might be able to test that because if you have a good R star and a photometric period, you also have V sin I.
Yeah.
So have you looked at that? Because if the model is correct, you should be able to just confirm that IMAG and V and I are the same.
Yeah, that's a great point. A lot of them do have existing V sin I measurements, just that other members of the collaboration did. Yeah, it was mostly for time reasons I didn't look into it, but that's a really good point and would be a great comparison.
Yeah, John has a question. Do you want to speak up for your question, John?
Oh yeah, sure. That's a great talk and really exciting, interesting results. I just wanted to circle back to one of the first topics you covered about how you measure the magnetospheric radius. And I think you mentioned, but I just wanted to confirm that it's from the total emission strength as well as the width of the hydrogen line. Is that roughly it, or did I miss something?
Yes, I think unfortunately I don't have a backup slide. The paper has a figure that shows the dependence of the hydrogen line profile on the magnetospheric truncation radius. And yes, the main change is the line flux. There's not a big change in the line width, actually. But I guess I should say we're also doing this analysis with normalized, like continuum normalized H alpha profile. So it's not in terms of absolute flux, but in terms of relative to the continuum. Yeah, did that answer your question sufficiently? Do you have a follow-up?
Yes, I guess the total emission strength also depends on the accretion rate.
Yes.
So I'm not sure how you separate those two, but I guess I should read the paper.
Yeah, so they do both absolutely affect the total emission strength. But when I did the actual looking for degeneracies, I looked for degeneracies in individual sources between the truncation radius and the accretion rate, as well as the big putting everything together for the full sample, and we don't see degeneracy between the accretion rate and the truncation radius. I am interested in general in looking into that more closely because it does seem like they should have some degeneracy. But at this point, they're not heavily degenerate.
That's great. Thank you.
Thanks.
I have a question.
Going back to the lupus, lupus 3 is the one that is a filament. The conclusion to have a non-uniform there, is it because it is a filament, or is it because it's not particularly affected by the shield? So the conclusion to have a non-uniform is particularly coming from the geometry or for some other external.
Yeah, that's a great question. I do think lupus 3 is kind of the least affected by those external forces. But I do think the clearest explanation to me is this kind of filamentary explanation.
When you say you're going to check if the other surrounding regions are non-uniform, are you going to look for specific filaments or just combine?
Just combined basically all the observations that are available. Okay, I think I also didn't include this in the backup slides, but in the paper, the appendix is much longer than the paper itself. I show measurements for Taurus, Orion, and Chameleon. And both Taurus and Orion's show some kind of evidence that it's not uniform there either. And those two environments are very different. So Taurus is like really kind of low density, low mass, not a lot of external irradiation, not a lot of massive stars around Taurus. Whereas in Orion, you have a lot of massive stars that, would be driving these wind bubbles and everything. So I do want to look to see if it's like in spite of external sources, external forces, or if those external forces are required for these correlations. Yeah, that's not clear yet, but something I want to explore. Thanks.
So related to that, do you have like a polarization observations for all these regions?
Mhm.
You mentioned that Lupus 3 definitely does.
Yes.
So I'm just wondering the magnetic field there, whether the inclination they are all related to the magnetic field.
So that was that's a little harder, I think. So in general, the 4 Lupus 4 regions do seem to be kind of connected to the magnetic field, and in the paper I show the magnetic field direction with each subregion. But these inclinations could be kind of anywhere. I mean, I guess for some of them we have the position angles, but the sample is fairly small that has both position angle and inclination. So that's not something that clearly popped out. But I wouldn't be surprised if it were related.
I think we do not have other questions now. Let's thank our speakers again. And Caeley will be staying with us today, and her schedule is shared with the urgent seminars email. So if you are interested to chat with her, there's still chance to.
Thanks again.